Hi, I'm Diane Kim from GIST, South Korea. I'm presenting Learning Architectures for Binary Networks, which is a joint work with Kunal Prathat Singh from IIT Roorkee and Jonghyun Choi, my advisor. As the below figure shows, our search architectures have a better flops to accuracy trade-off than most binarized floating point architectures. Taking a look at the binary networks in these similar flops ranges, the backbone architectures have a clear impact on the accuracy. However, not much research has been done on improving the backbone architectures for binary networks. We want to improve the backbone architectures used for binary networks. We could try various floating point architectures like most recent works on binary networks, but that's going to be difficult to tune for each individual architecture that we try. Instead, we want to search for binary networks using NAS methods, and specifically, we will be focusing on cell-based and differential search methods for their flexibility in the flops of the final search architectures and the computational efficiency of the search itself. We first tried out the most obvious method, binarizing architectures searched by various cell-based floating point NAS methods. Unfortunately, both training and test accuracy plummets after a few epochs, or in the case of darts, stays at 10% for the entire duration. From this observation, we see that direct improvement of the backbone architecture in the floating point domain may not translate well to the binary domain. To investigate why those search architectures didn't train, we checked the gradients during training. Interestingly, we observed that quantization error in the binary domain causes spiky gradients, which led to unstable training. So we want to reduce the quantization error when searching for binary networks. We first reduce the quantization error by defining a binary search space with already binarized layers as opposed to binarizing architectures searched in the floating point domain. In the process, we reevaluated common convolution layers that are used in floating point NAS. We built a small network composed of only one specific convolution layer and checked its accuracy drop going from floating point to binary. As the table shows, the regular and dilated convolutions show reasonable drops, while the separable convolutions drop their accuracy equivalent to random guessing. Hence, contrary to other popular floating point NAS methods, we decided to not use separable convolutions in our binary search space. In defining our binary search space, we also repurposed the zeroized layer. They are usually discarded from the final search architectures, even when they are the layers that the search algorithm picked. However, we do not discard them from the final architecture. We use zeroized layers because it is actually beneficial in cases like the presented figure, where the floating point output is small, but the binarized output turns out to be very big. In this case, it could be worthwhile to trade off network capacity for less quantization error by replacing the binary convolution with the zeroized layer. Here, we show the benefits of using the zeroized layers. We first note the performance improvement of zeroized layers as they reduce the quantization error. In addition, because zeroized layers cause exactly 0 flops, the network becomes much more resource efficient as well. Note that the inference speedup is higher than 64 because replacing a floating point layer with a zeroized layer offers much more speedup than just changing to a binary layer. In addition to our new search space, we also proposed a new cell template which is more robust to quantization error. We simply add skip connections from the previous 2 cells to the output of the current cell for better gradient flow. The figures here show the impact of our new cell template on the learning curve. The blue lines indicating the usage of our new cell template shows much more stable learning curves as both the train and test accuracy increase until saturation. In contrast, the green lines, which use the conventional cell template, shows an unstable learning curve where the training accuracy plateaus at a low value and the test accuracy plummets after a while. Not only that, an in-depth inspection of the gradients during training shows that the new cell template actually results in more stable gradients as well. Another unique problem we encountered was the extreme preference towards layers with no linear parameters, such as pooling, during the early search. This is because under-trained convolution layers are worse than pooling layers early on, especially in the binary domain. We found that diversifying the early search via an entropy maximizing regularizer with an exponentially annealed weighting helps to mitigate this problem. Our search architectures outperform the state-of-the-art binary networks when comparing just the backbone architectures. This indicates that simply swapping the architecture for our search ones can greatly improve the performance in various FLOPS budgets and use cases. Even when comparing to other methods that have other components and architectural improvements, we still obtain competitive performance. Note that through internal testing, we were able to obtain much higher accuracy by combining various training methods complementary to our architectural improvements.